Hi, my name is Ian Mallett. My co-author Jem Yuksel and I are at the University of Utah Graphics Lab. I will be presenting our work entitled Constant Time Energy Normalization for the Phong Specular BRDFs. Our paper is quite straightforward, but to sum up, the Phong BRDFs are an important class of BRDF. The Phong BRDFs have received lots of attention and even form the basis of other BRDFs. They are widely known and important within the graphics community and, although they have been superseded for production graphics purposes, they remain relevant for testing and education. Unfortunately, it is not known how to make the Phong BRDFs conserve energy exactly, which limits their usefulness. It is widely known how to make the Phong BRDFs not gain energy, but energy is still lost when the incident direction is not along the surface normal. The literature documents only a single algorithm to resolve this, but it is linear, or even quadratic, time in the specular exponent, and only works for integer-valued specular exponents. In this paper, we take that algorithm, apply mathematical transformations to it, and produce a new algorithm that is constant time and works for all specular exponents. Our algorithm, therefore, is the only general-purpose, efficient algorithm for computing the normalization constants for the Phong BRDFs. We hope this algorithm will make people consider using the Phong BRDFs more widely, and, if not, at least finally makes using them with correct energy normalization feasible for the first time for future reference. The bidirectional reflectance distribution function, or BRDF, is the standard way to describe how light reflects off of a surface. It describes the ratio of outgoing radiance to incident irradiance. The radiometric energy that hits any surface must all be accounted for, either by being reflected or by being transmitted and potentially subsequently absorbed. The ratio comes from the Fresnel equations. Therefore, the BRDF itself must describe how the energy is distributed within the hemisphere of reflection, but must not change the amount of energy that is reflected. Some BRDF models respect this, but many do not, because the correction factor is often extremely difficult to compute. Most BRDFs only ensure that energy is not gained. The standard term for this is energy conservation, although energy is not conserved, as it can still be lost. In this paper, we use the term energy normalization to mean that energy is neither gained nor lost, but is maintained exactly. We now focus on the Phong BRDF specifically. Much of the literature, including Phong's original work, predates the modern presentations, such as the rendering equation, that we adopt. See the paper for details. Also, while the original Phong reflectance model involved a Lambertian diffuse term, without loss of generality, we drop discussion of Lambertian, since that is easy to normalize. The original Phong specular BRDF is easy to express. It is just the light's reflection vector r dotted against the view vector, and the whole thing raised to some power. The max and the division by the geometry term are to correct technical issues. Please refer to the paper. The modified Phong specular BRDF is very similar. It is not clear which of the two BRDFs is more valid, so in this paper we simply consider both. Both BRDFs have a normalization term in front of them. This normalization term ensures that the BRDFs do not cause energy gain or loss. Our contribution is the calculation of these terms for the first time in a general-purpose constant time formulation. In almost every case when people talk about making Phong BRDFs energy conserving, they will invoke a well-known simple derivation. See the paper for details. Obtaining simple constant factors. Unfortunately, this derivation relies on the incorrect simplification that the light is coming in from along the surface normal direction. This makes the result correct for normal incidents, but incorrect in every other case. Intuitively, the problem is that the specular lobe tilts over, intersecting the ecliptic plane. The energy contained in that section of the lobe is lost, meaning that the result of the reflection should become larger to compensate. However, a constant factor clearly cannot do this. There is an alternative method, which we call Arvo's method, since it is derived fairly simply from a 1995 paper by Arvo that touched on similar topics. We present it here using updated notation. We will not be concerned with understanding where the algorithm comes from, nor even with how it works. The point is that it generates the normalization term for the Phong BRDF, and it does it correctly. However, we must also make a note of its limitations. First, the specular exponent lowercase n must be an integer. This is inconvenient, especially in the less specular, more glossy regime, where small increments are necessary, or when doing specular mapping, for example. Second, the algorithm has a loop in it. and that loop is linear in the value of the specular exponent n. This is an enormous practical problem since the specular exponent is often quite large. Again, this algorithm is correct as far as it goes, but the limitation to integers and the practical constraint of very low specular exponents makes it unsuitable for practical use. There is also a similar algorithm for the modified Phong BRDF. It has a few subtle differences, but has the same overall characteristics and limitations. Our contribution is fairly straightforward. We simply take Arvo's algorithms, combine them into a mathematical formulation, simplify the math, and then convert the result back into a practical algorithm. Most of our paper is concerned with the middle step of simplifying the math, because doing that is non-trivial and complex, and it is by far the hardest. We will follow a similar approach here, showing visually how the equations derive from each other. As a sneak peek, here are our final normalization factors. We would like to reassure the viewer that following each step in the derivation is not strictly necessary. Indeed, no understanding of the math is necessary to implement these final formulae or to use the simple example code we provide later. Indeed, these factors are less intimidating than they may look. First, we rewrite Arvo's method in terms of mathematical formulae. This is essentially just a tedious exercise in translation from code to math, and the translation is direct, besides some allowances so that the math works for both the Phong and modified Phong BRDFs. 2 points are of note, however. First, we have not removed the dependence upon the specular exponent lowercase n being an integer. We will explicitly relax this limitation later by continuation. More fundamentally, however, we will assume in the following that n is odd for the Phong BRDF and even for the modified Phong BRDF. This allows us to assume that k is even when computing the other terms. However, this is just for presentation clarity. It turns out we get the same result without this assumption. It's just a lot messier. Second, when written out in this form, the algorithm has jumped from linear time to quadratic time, since the s terms are computed from a sum with a linear number of terms, but each of those terms is computed using a linear product. This results in overall quadratic complexity. We now turn to analyzing the t sub k term. First, since we have assumed that k is even, we can eliminate handling the case. This can then be solved using basic techniques from complex analysis. Note that the double exclamation point is the double factorial function, which must not be confused with the factorial function applied twice. And the gamma denotes the gamma function. Unfortunately, this result seems impossible to simplify mathematically any further, but fortunately the ratio of gamma functions can be computed directly using standard library calls, so this is straightforward to compute directly. We now turn to analyzing the s sub k term. Again, since k is even, we eliminate the case. We now substitute in the t term that we just found. Solving this series is, unfortunately, extremely difficult. We break this series apart into a difference of two infinite series by fiddling with the start and end bounds of the series. The first infinite series can be solved by rearranging and applying the double factorial identity. When we do this, we see that we just have a binomial series, and binomial series are easy to solve. For the second infinite series, we first shift the series back to 0. Then, we rearrange and express the series in terms of the Pochhammer symbol. This is just algebra, there's nothing fancy actually happening here. The series can now be evaluated in terms of the Gaussian hypergeometric function. This can then be simplified slightly by using the special form of that function's arguments to invoke the incomplete beta function instead. It should be noted that this stage continues the discrete series, thereby allowing it to work with floating point arguments. We can now return to the problem of computing s sub k. We have just computed both subseries, so all we have to do is substitute them in to get an expression for s sub k. Now, finally, let's return to our expression for the normalization terms. Substituting in the appropriate s sub k, t sub k, and uppercase a terms produces, after a bit of simplification, our final normalization factors. Note that there is a detail relating to the numerical behavior of the term for modified Phong, which we defer to the paper. We admit that these normalization factors may look intimidating, but the code for implementing them is actually very simple. Indeed, the complete code is just a few simple lines. We provide a complete reference implementation here, in the paper, and in the supplemental materials. The only potential point of confusion in this code is the incomplete beta function. Since common platforms do not provide it, We demonstrate using the boost library here. Note that we must be careful to select the incomplete beta function, not the beta function. See the paper for more details, and the version in the supplemental materials for more comments. The visual results are fairly straightforward. Here, we see the damaged helmet GLTF test model, which we render with specular mapped Phong, or modified Phong. See also Figure 5 in the paper. With energy conservation only, the BRDF does not gain energy, but erroneously loses energy at glancing angles. This is more or less the previous state of the art. However, with our energy normalization term, we can see that the BRDF neither gains nor loses energy. The reflection is brighter, especially at glancing angles, and no energy is lost except where the artist intended for it to be absorbed. It should be noted that this alleviates one of the main cited difficulties with the Phong BRDFs, namely energy loss at glancing angles. We see that this was simply due to having lacked an energy normalization term. By adding our term, the problem is fixed. We demonstrate the performance when using our normalization term for the Phong BRDF in a minimal scene intended to show a worst case. See also Figure 4 in the paper. Our method adds only a few nanoseconds per path on top of the usual energy conservation term, and this behavior continues to any specular exponent. However, it must be noted that mere energy conservation is incorrect, whereas our algorithm, which does energy normalization, is correct. Therefore, they are not directly comparable. Arvo's algorithm, shown in red, which also does energy normalization, has comparable or slightly faster performance at low specular exponents. However, the improvement is small, while the limitation of Arvo's method to integer-valued specular exponents makes specular mapping problematic. For glossy and specular objects, we see that Arvo's algorithm also devolves into linear runtime, which is unacceptable and overall impractical. In conclusion, we have presented a mathematical reformulation of Arvo's algorithms that results, for the first time, in a constant time exact general-purpose algorithm for computing normalization factors for the Phong and modified Phong BRDFs. Our result is a bit tricky to derive, and the final formulae may look daunting, but the code is actually quite simple, and the benefits of true energy normalization make using our method an obvious choice with no real downsides. We hope that our normalization factors will make the Phong BRDFs more appealing, or at least will improve correctness whenever they are used. Thank you for your attention. There will now be a Q&A period.